CRT map.
Okay, so let me get started now. So let me just begin by mentioning that on the handout that I gave to you yesterday, I had a small typo at the bottom of it. So this was a result of the fact that I made it very early the morning of the talk. So the issue is that if you look at the contour, the two contour functions for the tree and dual tree, what has to happen is in each time step, one of them has to move. So you can't have a time step where they're both sort of constant. And if you remove all of those from the figure, then it should be correct in the end. Okay, so what I'm going to do now is I'm going to talk about the tool which allows one to convert random walk problems on random planar maps into what are more like random walk and random environment questions. And this is this mated CRT map, which I talked a little bit about last time, but I'm going to now explain how it works in a bit more detail. So the way it works is that you have some process xy, and this is going to be some type of Brownian motion or a Brownian excursion. And the parameter, just to remind you, is just the correlation between your Brownian motion and Brownian excursion. Or sorry, between the two coordinates of your Brownian motion or Brownian excursion. And which type of process you choose, which type of Brownian motion or Brownian excursion, this determines the topology of the map that you're going to be working with. Okay, so the type of Brownian process, this determines the topology. And there are a number of different nice choices that you can make, but the easiest one is the one I'm going to be talking about today, is the one where you have the topology of the whole plane. And the reason that this is the nicest one is that in this case, x and y are actually just going to be a genuine Brownian motion with some correlation. Okay? So in this case, you don't have to consider a conditioned process or an excursion. It's just going to be a Brownian motion. And what I want to do today is I want to explain how the mated CRT map is related to, and this is what actually provides its embedding, to SLE processes on Liouville quantum gravity. Okay? And the way that the parameters are related is, first of all, this parameter kappa is always going to be bigger than 4, and gamma for the Liouville quantum gravity is going to be 4 over the square root of kappa. And the covariance or the correlation in the mated CRT map is going to be minus cosine pi times gamma squared over 4. Okay? And just to remind you of how the definition works, so what you do is you start off with a copy of the integers. Okay, so the vertices are going to be given by the integers, and then we're going to say that they're adjacent if a certain condition holds, and the condition is that if you look at the infimum of the values that x takes on between the interval x minus 1 and x. So here my integers are x and y, where I'm going to assume that x is smaller than y for simplicity. So what you need is that the maximum of this and the infimum that x takes on in the interval from y minus 1 to y, this should be less than or equal to the infimum that x takes on when t is in the interval from x to y minus 1. Okay? So two vertices are going to be adjacent in the integers if this condition holds, or the same is true with y in place of x. Okay? And just to remind you that this definition comes with a very nice picture. So this is exactly the same thing as this picture I drew last time, where you take your two processes, x and y, and you just draw their graphs. So let's say this is the graph of x. And then you do the same thing with y, except for you like to draw it upside down. And then you can think of each vertex in the mated CRT map as corresponding to a stripe. So you have these vertical stripes, like this. Oops. No, that was okay. So you have these vertical stripes, and each stripe is going to be a vertex in the map, and it corresponds to an integer. And these vertices are going to be adjacent to each other when you can draw a chord which connects them, which goes either below the graph of x or above the graph of y. Okay, so this is the random planar map model, and the theorem that allows us to view this as an embedded planar map. This comes from the mating of trees, and this is actually the main theorem from Liouville quantum gravity as a mating of trees. And what the theorem says, roughly speaking, is that if you take an SLE kappa process and you put it on top of Liouville quantum gravity, then this encodes exactly the same information as this Brownian process x comma y. Okay? And so what I'm going to do is I'm going to explain this now in a bit more mathematically precise language. But the point is that this tells you that the mated CRT map, this has an embedding, a natural an embedding at least that one can construct into the plane. Okay, and this is what allows you to start doing calculations. Okay, so at this level, this is a bit abstract, so I want to try to explain to you how one makes this a bit more mathematically precise. And to start to do that, so to make this precise, what I need to do is I need to specify two things. So number one, I need to make it precise what type of Liouville quantum gravity surface I'm going to put my SLE on top of. And secondly, I also need to tell you exactly what the type of SLE process that we're going to be using here. Okay? Okay, so just before I do this, let me just give you a very, very brief reminder of Liouville quantum gravity. So in Liouville quantum gravity, you have some kind of a planar domain. So D is some domain in the complex plane. And you have this field H, which is a Gaussian free field like distribution. And you have at least two objects that you can define in a relatively straightforward way. So you have the area measure. Let me call this mu h. And roughly speaking, this is what you get when you take Lebesgue measure and you have the density e to the gamma h, where h is your Gaussian free field like distribution. And to make this precise, one way of doing it is that you can take the limit as epsilon goes to 0 of epsilon to the gamma squared over 2 times e to the gamma h epsilon of z dz, where here h epsilon is the average of the average of your field on the boundary of the ball centered at z of radius epsilon. Okay? And so you have this area measure, so you can compute areas of regions. And you also have a boundary length measure. And the boundary measure, this is what you get when you take, again, Lebesgue measure, but now on a line rather than in the plane. Okay, and the Radon-Nikodym derivative here is going to be e to the gamma h of z divided by 2. Okay, so this is, again, Lebesgue measure. Okay, but on something like a line segment rather than in the bulk of your domain. Okay, and let me quickly remind you of two other things. So one of them is the coordinate change rule. So how does this work? So here you've got two domains, d and d tilde, and you have a map which is conformal and goes from d tilde to d. So this is a conformal transformation. And the coordinate change rule says that if you let q be 2 over gamma plus gamma over 2, and you define h tilde to be h composed with phi plus q times the log of 5 prime, then what's going to be true is that mu h of phi of a is equal to mu h tilde of a for all sets A, and the same thing for the boundary measure. So mu h of phi of a is equal to mu h tilde of a. Okay, so this is how coordinate changes work in Liouville quantum gravity. And there's a very important definition, and this is the definition of a quantum surface. Okay, and the way that a quantum surface is defined is the sort of idea is that you have many different possible ways of parameterizing a Liouville quantum gravity surface. And so you say that d tilde h tilde is going to be equivalent to dh if the fields are related as in this equation here, okay? And a quantum surface is just an equivalence class under this equivalence relation, okay? And, right. Okay, so now what I want to do is I want to explain to you the particular type of quantum surface which comes up in the main mating of trees theorem. And this is something called a quantum cone. And this is going to be a quantum surface with the topology of the whole plane. So this is has the topology of the plane. And with these quantum surfaces that come up in Liouville quantum gravity, often the definitions can be a little bit complicated. And so it's often not very instructive just to write down the definition. It's actually much more helpful to think about where the definitions come from, or how do you derive them. And because this is an example of a very common theme in the area. And so here what you do to derive the quantum cone, and this is sort of what you always do, is you try to mimic what happens when you work with random planar maps. So in this particular case, you're just going to mimic the construction of the UIPT or the UIPQ, but you want to do this in the context of Liouville quantum gravity. Okay. So this is the idea. So let me explain how this works in a bit more detail. So the way that you construct the UIPT or the UIPQ is very simple. So to construct, for example, the UIPT, what do? You sample a finite volume, random triangulation, with some fixed number of vertices. So for example, with n vertices, you then pick a random vertex inside of your map, and then you look at what happens when you take a limit. You take an infinite volume limit okay, and and what you try to do is you show that finite neighborhoods, so finite neighborhoods of your point, these converge in the limit. To some kind of limiting random graph. Okay, so you take this kind of Benjamini-Schramm limit as the size of your map goes to infinity, and to construct a quantum cone, basically what you're going to do is you're going to do exactly the same thing, but in the context of Liouville quantum gravity. Right, and so how does this work? So to do this for Liouville quantum gravity, you have to be able to do two things. You have to be able to pick a point at random, which is going to be the analog of picking a random vertex in a random triangulation, and this is going to come from the Liouville quantum gravity measure. And you also have to decide how you're going to take the infinite volume limit. Okay? So I want to try to explain to you how this works, because once you sort of see that this is the right procedure to perform, then it's not so difficult to derive the definition, the sort of right definition of this quantum cone. So let's suppose we have a domain in the complex plane. It's not going to matter which one, and we have any Gaussian free field-like distribution, like perhaps just the Gaussian free field, on our domain. And for simplicity, it's a little bit nicer if we assume that the measure, the Liouville quantum gravity measure of our domain is finite. Okay? So what are we going to do? So we're going to pick a point. So let's say this is our domain. So we're going to pick a point in the domain from the Liouville quantum gravity measure. Okay? And then what we want to do is we want to zoom in around this point and understand what the local picture is converging to. Okay, so we're going to zoom in near Z, and so what is the right way to do that? So what you do is you want to perform a certain type of rescaling And the point is that if you have a constant c, so if c is some positive constant, actually it could be any real constant, and you take your field and you add the constant c to it, then the way that this is going to transform is this is just going to become e to the gamma c times your measure associated with the original field. Okay? So what you can do is you can translate by minus z, so that z goes to the origin. Okay, and then you want to rescale so that the disk has 1 unit of mass. Of Liouville quantum gravity area under the measure where you've added the constant c, and then you just take a limit as c goes to infinity. Okay? And this is sort of the most natural way that you can think of to take an infinite volume limit in the context of Liouville quantum gravity. So if you just think about it on your own, you know, this is really the only procedure that makes sense that you could possibly come up with. And the result of this is going to be the quantum cone. And again, it makes sense because this is exactly the same thing as what you do to construct the UIPT or UIPQ in the context of planar maps. And so again, you're going to get this quantum cone. And the quantum cone is, it's a Liouville quantum gravity surface which is parameterized by the whole plane. And it has two special points. So you have a special point at the origin. So this is kind of like your origin in your quantum cone. And this is going to be special because this arose as the infinite volume limit around a point chosen from the Liouville quantum gravity measure. And you also have this special point at infinity. Okay? And I don't want to write down the actual mathematical definition of the field that you get, but let me just say that roughly speaking, so very roughly, the field that you get is like a whole plane Gaussian free field, except at the origin you have a minus gamma log singularity. And the reason that you have this is that this term here, this arises because this is near a quantum typical point, so near a point chosen from the Liouville quantum gravity measure, you always have a minus gamma log singularity. Okay? So this is, roughly speaking, the object that you get, but this is exactly where it comes from. So it's just the most natural kind of infinite volume limit. Okay, so this is one half of the story. So the other half is making precise exactly the kind of SLE process which is going to arise. And the SLE process is going to be describing a curve which is a piano curve snaking between two trees. And this is a variant of SLE. Yes?
When you say you as 1 unit of gamma LQG area,
yes.
For 1 unit for mu h plus c, right?
Yes, exactly. So the point is you use this measure
this
here.
This is a zoom.
Yes, exactly.
Mostly it's like taking a disk of size epsilon a bit.
Yes, that's right. So it's a disk of random size. but its size will be going to 0 when you make C larger and larger. Because if you look at...
C goes to infinity is like making the actually...
Yeah, exactly. So if you go back to the original picture, here, and this is your point Z, then, under the original measure, you want this to have mass e to the minus gamma C. So the size of it's going to get smaller and smaller. But it's going to have a random size. Yep.
Is there a description in terms of approximation of the GFF? If you took an H epsilon,
Yes.
is there a simple description of?
The quantum cone? Yes, the quantum cone is actually not very difficult to describe. I can write down exactly what the distribution is, but I wasn't going to do it because it takes a few extra minutes to write it down, and the definition is slightly complicated. There's a slight complication.
The question was different. If you try to do it starting from the approximate,
Yes. Yep.
the limiting procedure, you could do that, for example, just conditioning. Is it the field conditioned on the value at the point Z that you have sampled according to the measure?
So if you did it with the H epsilon measure, it would be like choosing a point, from the field mu H epsilon. And you can write down exactly what you're going to get again, and it's going to be almost exactly the same as this, except for instead of having minus gamma log, you're just going to have a truncated version of the Green's function.
So it's like conditioning on the value at that point.
Yeah. Yeah, so this is something that you can also do. Yep. Okay, so this is the field that arises. And now let me take a moment to describe to you the SLE process. So this is something which is called space-filling SLE. And this is a process which is this is defined, and it makes sense for whenever kappa is bigger than 4, okay? And again, what this is it's the piano curve, which is associated with a certain pair of random trees. And the trees come from the Gaussian free field, so it's associated with the tree dual tree pair of Gaussian free field flow lines. Okay, so this is how the actual construction of this comes from the SLE Gaussian free field coupling. I don't want to go through the rigorous construction, but let me just explain that when kappa is greater than or equal to 8, so this is the regime of values where ordinary SLE is space filling. It's going to be the same as regular SLE, because SLE is already space filling. And the way that you can think about it when kappa is between 4 and 8 is that it's obtained by taking a regular SLE and SLE kappa. And remember, when you're in this range, regular SLE is not space filling, but it does intersect itself. So it can, as you go, it does sort of this. So that would be like a regular SLE kappa. And what space-filling SLE does, which is different from regular SLE, is that as you go along, you're going to cut off bubbles from infinity, for example, at this time here. And rather than continuing on and going on to infinity, what you're going to do is you're going to branch in and somehow fill up this bubble. And then after you've finished it, you will continue on like your regular SLE, except you always are filling in these bubbles that the regular SLE is cutting off from infinity. And basically the role that the Gaussian free field plays in the construction of space-filling SLE in this regime is that it's not actually a priori clear that somehow this process of filling in the bubbles that you cut off from infinity is actually going to define for you a continuous curve. And so somehow the proof of continuity depends strongly on the SLE Gaussian free field coupling, but you can describe what the object is sort of directly. Okay? Yep.
So you've drawn it in the upper half plane, but the ones you want to work with are in the full plane.
Yes, that's right. Yep. Yeah, so this makes sense in different types of domains. Ultimately, the one that we're going to care about is the whole plane version of this, but this also makes sense if you're in any other simply connected domain. Okay? Okay, but the point is that when kappa is between 4 and 8, the space-filling SLE doesn't make sense as a Lovener evolution, and so you have to construct it and describe it in a slightly different way. Okay, and then as Ellen actually just sort of foresaw, so here what we're going to need is a version of this which is not in the upper half plane, but we want a version of this which lives in the whole plane. Okay, so we want the whole plane version. And for what I'm going to be talking about, it actually doesn't really matter what regime of kappa values you're looking at. And so it's much easier just to think about the case where kappa is greater than or equal to 8. Because for these random walk techniques, it really doesn't, it's just sort of an extra complication to think about the case when kappa is between 4 and 8. And the whole plane version of space-filling SLE, for this regime of kappa values, is fairly easy to describe. It's going to be a random curve which is defined on the real line, and it goes into the complex plane. And the natural way to parameterize it is just by Lebesgue measure. You just parameterize it by area. And the way that it's sort of characterized or singled out is by a very simple Markov property. So it's characterized by the property that for any given value of t, so if you give me any time t, then it's going to be true that the conditional law of the curve after time t given the realization of the curve up to time t is just going to be an SLE curve. So it's just going to be an ordinary SLE in the remaining domain. So in this case, it's going to be the complex plane minus the curve up to time t. Okay? So the picture that you should have in mind is that you have this curve defined on the whole plane. And if you run it up to any time t, it's going to look something like this. So this is like the range of the curve from time minus infinity to t. And the complement of it is going to be a simply connected domain. So the complex plane minus the curve up to time t. And the conditional law of what you see here is exactly going to be an SLE kappa curve starting from eta of t and going off to infinity. Okay? And yep.
And you also just say that it's in the same way when you zoomed in at the near typical.
Yeah, exactly.
The usual half plane one, and you wait until you hit one, and
yes, exactly.
there,
That's right.
You get
Yep.
the whole plane.
Yes, that's right. So this one you can construct directly and see it's continuous in exactly the same way that Vendelin said. So if you take a usual SLE kappa going from x to y, and you pick a point, then you can define it by running your space-filling SLE up until it eventually hits this point z, and then you can take an infinite volume limit, and it will converge exactly to this picture.
The same is true for the kappa small n.
Yes, the same is true for the kappa smaller than 8, but it's still a challenge to prove it's continuous to begin with. Yep. Right. Okay, so this is the SLE process. And now let me tell you the state the theorem. This is a more precise version of the mating of trees theorem. So this is this theorem from the mating of trees, which is this this paper with Scott and Bertrand. And this is what gives you the embedding of the mated CRT map into Liouville quantum gravity. And what you do is you take your quantum cone. So this is your Liouville quantum gravity surface. And then you're going to sample an independent SLE process. So this is sampled independently of the quantum cone. And then what you're going to do is you're going to reparameterize the SLE after sampling it so that it fills 1 unit of Liouville quantum gravity measure in each unit of time. So that so what you want is that mu h of eta from time s to t, this is going to be equal to t minus s for all s less than t. Okay, so again, the SLE is sampled independently of the quantum cone, but after sampling it, you then reparameterize it so it satisfies the condition that it parameterizes 1 unit of mass in each unit of time. Okay? And so what does the theorem actually tell you? So it says that it's going to describe the evolution of the boundary lengths of the SLE process. So the picture that you should have in mind is that, let's say this is the origin, and you have your SLE up until it hits the origin. So maybe this is eta of minus infinity 0. So I'm assuming that it hits the origin at time 0. And then what you can do is you can imagine that you run it for 1 more unit of time. So then it will be, let's say, here. Okay. So this is going to be this sort of chunk is eta from time 0 up to time t. And then what we're going to do is we're going to look at how the boundary lengths, the Liouville quantum gravity boundary lengths of this SLE are evolving. Okay? So x sub t, this is going to be the gamma Liouville quantum gravity boundary length of the left side of the curve. So it's going to be of the left side of your the boundary of your curve from time 0 up to time t, minus the curve from time minus infinity up to time 0. Okay, so this first thing that I've just defined, this is the boundary length of this chunk here. And we want to look at how this compares to the Liouville quantum gravity boundary length of the boundary of the chunk, but this time intersected with the boundary of the past. Okay, so what we're looking at is the difference of the red thing here minus the blue part. Okay, so this is what x sub t is keeping track of as you change t. Okay, and then what you do is you define y sub t in the same way. So this has the same definition, but with right in place of left, and the theorem tells you what kind of process you're going to get. So it tells you that x sub t, y sub t, this is going to be a Brownian motion where the correlation between the two coordinates is given by minus the cosine of pi times gamma squared over 4. Okay, so this is exactly the process that you see when you define the mated CRT map. So this is sort of exactly where it comes from. And this theorem, so one way of thinking about it is that it gives you a way of sampling the mated CRT map using SLE and Liouville quantum gravity. Yep.
Your x is going to be just a standard Brownian motion, or there's no scaling?
Yeah, so that's actually an issue, but the scaling is actually not going to matter. So the speed is the same for x and y, but I'm not saying what the speed is. So identifying the speed of the Brownian motion is actually an interesting question, which is not answered in that paper. Yep.
Just something I missed. It's just so the cone is equipped with an area measure, and the boundary length in the cone is also easy to define.
Yes, that's right. Yeah, so there's actually a non-trivial thing which has to do with defining boundary lengths of SLEs, but that's something which one can do, and this is something which is accomplished in Scott's paper in the quantum zipper. So there is a way of defining boundary lengths of SLE curves. So you do have a Liouville quantum gravity boundary length. Okay. So this is the theorem which is going to give us the environment that the random walk that we're going to be looking at is living in. And it gives you a visual way of representing the mated CRT map with an embedding into the plane. Okay? So how does the mated CRT map work? So the way that it works is that its vertices which sometimes we call cells. These are going to be the chunks of space that the SLE explores between integer units of time. Okay, so between, say, time x minus 1 and x, where x is an integer. Okay, and the adjacency relation in the mated CRT map tells you that cells which correspond to, let's say, times x and y. So these are these give adjacent cells. When it's true that the boundary of one cell intersected with the boundary of your other cell, when this intersection, this contains a non-trivial boundary arc. Okay, so let me draw a picture of what this looks like. And by the way, this is actually also one reason why it's much nicer to work with SLE kappa when kappa is bigger than 8, because then it's much easier to draw and to visualize the cells, because they can start to be quite complicated once kappa goes below 8, and in particular once it gets very close to 4. Then the topology is much more complicated. But when kappa is greater than or equal to 8, the picture is pretty simple. So you imagine you have your SLE coming along, and let's say it's made it to here by time 0. So this is your path from time minus infinity to 0. And now I can start using it to construct the cells in my mated CRT map. And I imagine I run it for one more unit of time. And maybe it gets to here. Okay? So this is going to be the cell which corresponds to the integer 1. And maybe I'll color this one blue. And then you run it for one more unit of time. And maybe it goes over to here. And you get another cell, which looks like this. And you keep running your SLE each time for one unit of time. And you will keep generating these successive cells. Okay? Now, in reality, the picture is much more complicated than what I've drawn here, because the time parameterization comes from the Liouville quantum gravity measure. And so what this means is that each cell is not going to have approximately the same size. What can happen is that you have some cells which are extremely small in the Euclidean sense. So it could very well be that you have something that looks like this, which is right next to a cell which is much larger. Okay, so there's always this this possibility, and this is one sort of serious complication in the analysis. So this time parameterization is going to be very important. Okay. And again, the reason for this is that it's possible, and it does happen, that the cells have they can have very different Euclidean sizes. Okay, and this again, this significantly changes the analysis, because we want to do random walk on these cells, where each one is going to correspond to a vertex. Let me just remark that if you consider a different question, so if you instead define your cells, if you were to define your cells using Lebesgue measure, instead of the quantum gravity measure, then the analysis is actually significantly easier, because it's still going to give you a random graph. This will be a random graph in the plane. But the difference is that space-filling SLE turns out to be a very regular process. So the cells will still have random sizes. Some will be a bit smaller than others, but they're not going to be that different. Okay? So you're going to get a lattice. You're going to get a much more regular graph. And for a graph of this type, I don't think it's really a significant challenge to start to apply, the standard random walk and random environment machinery, because again, you don't have this issue where cells size are changing so much. Let me make one other remark about this. So the types of tools for analyzing this, once you get to this point, you can actually apply them in much more concrete settings. So there are other types of graphs which have a very similar flavor, which you can define much more quickly and directly. And the same sorts of techniques are going to apply. So there's another graph. So this is a very closely related construction, which is somehow much more concrete, but it suffers from some of the same problems. So what you can do is you can take a Liouville quantum gravity surface, like a quantum cone, or maybe even on just a domain D. Let's say you have some kind of bounded domain, perhaps, and you have a field on it. And if you fix a positive parameter delta, then what you can do is you can divide your domain, or subdivide your domain into dyadic squares. And the way that you do it is that you take, about each point, the first square whose mass falls below delta. Okay, so this will give you some kind of random tiling of your domain, and you'll have this effect where you have some very big squares and you have very small ones, etc. Okay, and in terms of the analysis, this kind of graph is something that you can arrive at very quickly, and the same types of tools are going to work here as they're going to work for the space-filling SLE one. The difference, and the main difference, is that you really have to analyze the space-filling SLE one if you want to make conclusions about random planar maps. But in terms of the random walk and random environment type tools, this is a perfectly fine example which suffers from all of the same challenges. Okay. So again, the sort of goal in all of this is we want to use these tools, or these representations, ultimately to say things about random walks, in particular random walks on random planar maps. And so what you need to be able to do, for example, is you need to be able to compare or compute Dirichlet energies of harmonic functions. And you want to compare harmonic functions where you're looking at harmonic functions which are harmonic in the Euclidean sense, and you want to understand how they relate to functions which are harmonic in this kind of random graph, or the one that comes from SLE. And for some things, this actually reduces to relatively simple moment calculations. And there's one particular moment which is extremely important. And this comes up in several different contexts in these works, and it's the following. So let's suppose that I have a function f, and I'm going to assume that this is a Euclidean harmonic function. Okay? So if I have a function which is harmonic in the Euclidean sense, I can use this to, induce a function on the mated CRT map graph. And of course, you have to make a choice when you do this, because you have to decide, what value your function on the graph is going to take based on the Euclidean harmonic function. And there are a variety of different ways of doing it. So one simple way of doing it is if you have one of these cells, essentially it's not really going to matter. I mean, you can just pick, for example, the center of mass inside of your cell, and you can define the function that you want to analyze on the mated CRT map to have the value on the cell just to be equal to the value of the original function at this center of mass. Okay, so but you could really choose this point in any way that you want. And then what you want to do is you want to understand how this function behaves. And in particular, for the purpose of analyzing random walks, you want to get a bound for Dirichlet energies. Because if you get a bound for a Dirichlet energy for a function on your graph, then that of course gives you an upper bound for what the actual harmonic function, the Dirichlet energy obtained by the actual harmonic function with the same boundary conditions on the original graph. And so you want to look at something like, the Dirichlet energy of this this function that I've defined, f bar. So let's say, you want to look at something like this, and here the sum is over cells x and y, which are adjacent to each other. So this is how the Dirichlet energy is defined. And if you want to get an upper bound, it's a little bit nicer if you just take an expectation of this. And because this f here, this was it came from a Euclidean harmonic function. So this is something which is essentially a smooth, very nice function. And so this is basically the same thing as taking an expectation of the sum over your cells, and you have x adjacent to y, and let's say it's an upper bound. If you just replace your function by its gradient, evaluated at some point inside of your cell, and then you just take, you replace this difference just by the product of the diameter squared and the gradient squared. So you have something like this, okay? And there's sort of a standard trick whenever you're in this situation, which is, I'll explain after doing one more step. So I can replace this with just a sum over cells, but not over pairs of cells, just a single cell. And it's only going to get bigger if I do this, and I add in the degree, okay? And this is going to reduce to what turns out to be an extremely important moment bound. Namely, whenever you're confronted with something like this, kind of what you always do is perhaps the same thing, which is you can rewrite the sum as an integral. So this is the same thing as taking an expectation, and then rather than summing, I'm just going to integrate. And then, in order to turn this into an integral, I have to deal with the change from summation to integration, which means I need to divide by the area of my cell. So here h sub z is just going to be the cell which is containing z, okay, and multiply it by the degree. Okay, so this is representing the same thing. And now, if I chose my function to be deterministic, so f is a deterministic harmonic function, then I can switch the order of everything, and you just see the expectation of the diameter, the ratio of the diameter squared of your cell to the area times the degree. And this is now this is actually kind of a much more concrete question now. So you have something like your SLE on your domain or the whole plane. You pick a Euclidean point z, sort of a Lebesgue typical point z, because I'm integrating with respect to Lebesgue measure. I'm going to have some kind of cell which contains that point. And to start to say things about harmonic functions on the mated CRT map, I just need to control the ratio between diameter squared and area. So this is kind of like how long and skinny is the cell times the degree. And again, this is something that you can actually control. And once you do that, then you can start to prove things about harmonic functions on the mated CRT map, which then translates into harmonic functions on random planar maps. And what I'm going to try to explain next time is it turns out that this type of condition is also exactly the right condition that you need to look at in order to imply that if you do random walk on top of this type of environment, you will actually have an invariance principle. So particularly, you just have to show that something like this is going to be finite, and this will imply that not only is the random walk sort of nice, it's going to go to some kind of a Brownian motion. Okay, and so I think this is sort of where I wanted to stop. Yep.
So you're missing a square and the gradient, and then what you want to say
yes.
is what you want to say is somehow that the diameter, this thing with depend on z on the right does not depend on z. You could
yeah, that's right. So yeah, that's right. So the point is that as long as you're, for example, in the context of the quantum cone, as long as your z is a little bit away from the origin point, then you don't see it, and this is just going to be a constant. And once you can control that type of constant, then you can prove lots of things about random walk. In particular, next time I'm going to focus on the central limit theorem, showing that it actually goes to a Brownian motion.
Thank you. Any questions? So maybe let's thank Jason again. So we resume in 15 minutes.